Tech from Model Engineering College, Trikakara in VLSI and Embedded Systems, and her graduation from VLBG CET Coimbatore. And she had started her career in teaching from 2004. Ma'am, now we can start the session.
Okay, thank you. I will just share the slide. Good afternoon, everyone. Here we are for the second session of VLSI Module 2, Module 4. And this is a part 2 of this module, which is the last part. Now, today we are going to deal with transmission gates. So this is just an overview of what we are going to see today. Initially, we'll try to define what transmission gate is. How can we analyze the working of a transmission gate? And next, what we'll see is how to implement logic functions using transmission gates, just like how we have seen for past transistors. And after that, we'll just see a small DC analysis where in which we are trying to find out the equivalent resistance of a transmission gate. Now, why that is used and where that is used, we'll see once we finish off initial two portions. Okay, so we can start. So transmission gate basically forms the last part of module 4. Now, earlier in the first session, we have seen working of a pass transistor. We have seen working of a complementary pass transistor logic. So why we go for transmission gates, or what are basically transmission gates? So we'll start from pass transistors. We have seen that either an NMOS or a PMOS can act as a pass transistor, and it can be used to implement logic functions. So the major characteristics, or as such the disadvantage of using an NMOS is that NMOS can give only a good 0 and PMOS can give only a good 1. So when it comes to giving a good 1, NMOS cannot give a good 1 and PMOS cannot give a good 0. So that was a major disadvantage we have seen for past transistors. So transmission gate actually tries to overcome this disadvantage of past transistors. So transmission gate also can be used to implement logic function just like how we have seen for past transistors. In addition to that, whatever disadvantage is there in the past transistors is actually not there in your transmission gate. So basically, transmission gate is nothing but a switching element. Just like past transistors, we have seen past transistors is either an NMOS or PMOS, you can use it as a switch, right? The transmission gate is also a switching element. So there, what you have is NMOS and PMOS together and they are connected in parallel. So transmission gate is a switching element which uses both NMOS and PMOS connected in parallel. So since you are having both NMOS and PMOS in a single circuit, it combines the advantage of both. So thereby transmission gates we can say transmission gate can easily pass both 0 and 1 very well. So thereby it can be used as building blocks for logic circuitry. So that is just a glance of what your transmission gate is. So the basic idea is transmission gate is nothing but a switching element and it has both NMOS and PMOS connected in parallel. And such circuits are used to implement logic circuits. So as I told you, here I am having a NMOS and to this NMOS, we also have a PMOS connected in parallel. So this is just a transmission gate. Okay. So what happens is on the left hand side, what you have is an input. That is, I've connected the terminals or the inputs of both NMOS and PMOS. I've shorted together and taken as input. And the output of PMOS and NMOS are shorted together and taken as output. Or more clearly, I've just I've just rotated the diagram. This is one way of looking into it. So you have a NMOS here, you have a PMOS here. So remember, wherever you are having a bubble, that indicates that is a PMOS. That is indication or symbol of a PMOS. So here you are having an NMOS, here you are having a PMOS. This is my input and this is my output. Now one thing to note here is, if you have to note the gate signal. If I am providing A as a gate signal for one of the gate, either NMOS or PMOS, for the other one should be the complement of it. So if it is A here, the other one is A bar. Or suppose if it is A bar here, the other one is A. So that is basically how your transmission gate is. So the gate signals are basically complement of one another. That's how it should be. And then you are having input and then you are having the output. So this is basically how, when I said NMOS and PMOS are connected in parallel, this is how it is connected in parallel. So more clearly, by defining or by looking onto how the source and drain are connected, this is how your transmission gate looks like. That is, for an NMOS, the drain and the PMOS source are shorted together and given as input. Same way, the NMOS source and PMOS drain are shorted together and taken as output. That is more clear definition, or that is more clear idea about your transmission gate. So this is how, or this is your basic transmission gate. Now we'll just see normally in textbooks how or what symbol do we use to represent your transmission gate. So this is a symbol of transmission gate. 1 minute. This is a symbol of transmission gate. So where you put a bubble, that is normally the transistor PMOS. Where you don't have a bubble, that is your NMOS. So this terminal basically indicates the gate terminal of PMOS. And the opposite side is the gate terminal of NMOS. On to the left hand side, what you have is your input, and the right hand side, what you have is your output. So this is the general symbol, that is a symbol of transmission gate. This is a basic symbol of transmission gate. Now we'll come back to this diagram. This you can say the circuit diagram. So we'll just see how your transmission gate works. Okay. So here in this case, what I've done is, for an NMOS, I've connected A as your gate signal. For a PMOS, I've connected A bar as your gate signal. Now imagine the condition where A equal to 1. If A is 1, A bar is 0. So when A is 1, 1 is given to the NMOS gate and 0 is given to the PMOS gate. So that means both of the transistors are on, if you remember. So both of the transistors in this case is on. So what will happen is, whatever input you are giving, since both the transistors are on, it gives a low resistance part to the output. So whatever input you are giving is transferred right away to the output. Okay, so that is the basic working of a transmission gate. Now imagine the other case where your A is 0. When A is 0, gate value or gate terminal is 0 potential, and a gate of PMOS is at A bar. It is A bar, so this is 1 here. So you're having a 0 to gate it to the NMOS and 1 to gate of the PMOS. So what happens is, both the transistors are off. In that case, you can say the output is actually disconnected from the input. You cannot say what the output is, or normally you call that as a high impedance state. So that is the basic working of a transmission gate. Now initially itself I told you, transmission gate, since it has both PMOS and NMOS together, it can effectively give 1 and 0. It's not like you have an NMOS alone or a PMOS alone. So how does that happen? Imagine the case where gate are active. Both the gates are active. So that is a condition where your A equal to 1 and A bar equal to 0. So this NMOS is on, PMOS is also on. Okay, so you're giving an input. The input can be either 0 or 1. Imagine you are giving the input as 0. So this is just a switch. So it just transmits that 0 as it towards the output. So what happens is, when you give a 0, this PMOS is also on, NMOS is also on. Am I right? Now we know, like in past transistor section, we have seen that a PMOS cannot pass a full 0, because by the time the voltage come back to VTH, this PMOS will be off. But NMOS, when you give a 0 here, this transistor is always on. So what happens is, no matter what the input voltage is, this NMOS will give a low resistance path to the output. So this entire 0 is transmitted to the output. But whereas as the voltage decreases to VTH, this PMOS will be off. So PMOS is off means this will give a high resistance path, so that entire 0 cannot be transmitted through the PMOS. So that is a basic idea I say. transmission gate can give a good 0, and also same way transmission gate can also give a good 1. How? We look into that. So for a good 1, say input is again 1. So both the gate are active. That means this NMOS is on, PMOS is on. So if we give a logic 1 here, if you look into the NMOS and the PMOS section, we have seen that in past transistors, this NMOS, it will not give a proper 1, because once the output reaches a value VDD minus VTH, this NMOS is off. So NMOS is off means it will give a high resistance, but PMOS is always on. So thereby it will give a low resistance path between the input and the output. So the entire one can appear at the output. So that is the reason why whether the input is 1 or 0, this transmission gate can effectively or faithfully give the entire output, okay, as 1 or 0. So the major issue regarding pass transistors is solved out here. So that is a basic working of a transmission gate. So we have just drawn the transmission gate truth table. This is a symbol of the transmission gate. Now one thing you always have to remember is, wherever you are having a bubble, that is an indication of PMOS gate. Okay, so don't confuse this and this with the bubble. These are the nodes. So here is where your bubble is. So that means this is a gate of your PMOS, and opposite side, obviously that will be the gate of your NMOS. So here in the circuit, my input is A and my output is B, and the gate signal, I've named it as control. So for the NMOS, it is control, and for the PMOS, it is control bar, right? So what happens is, like we have analyzed the circuit earlier, when control is 1, then your NMOS is on. If control is 1 means control bar is 0, then your PMOS is also on. So your input is transmitted on to the output only when control bit is 1. So depending upon that, you are having a truth table here. So let's look into the truth table. What all I have? I have here control, I have the input A, and I'm having the output B. So control is my gate signal. So only when control signal is active, that is it is 1, your input is transmitted out to the output, right? So we'll see that here. What happens when control is 1? You're having two cases for control as 1, because the input is A can take two values, 0 or 1. Am I right? So what happens when control is 1 over here? This NMOS is on, PMOS is also on. So what will happen if I give A value as 0, A as 0 here, then through the NMOS, it will show in the output B. So output B will be 0. Similarly, if the control is 1, both the gates are active. Control is 1, control bar is 0. So both the transistors are on. And if I give the A value as 1, then that one will appear through the PMOS as output at B. So that's what your truth table is about. Now imagine the other way around. You are making the gates inactive. So that means you're giving control value as 0, or you can say that you can see that as C. Here it is control. So control, you are assuming or assigning the value as 0. So control bar is 1. So anyway, both the transistors are off. So no matter what value you give for the input value can again change as 0 or 1. No matter what value you are giving it as input, your output will be always not defined, or you normally say that is a high impedance state. So this is just the idea of working of a transmission gate. Okay, so just like how we have seen for a pass transistor, for transmission gate also we can write an expression or Boolean expression for the output. So in this case, B is your output here. So the idea to write the equation for B is, or the output is nothing but like what we have seen for pass transistors. It is nothing but input A multiplied by or A dot C or control here. So Boolean expression B equal to A dot control, A dot control. So one thing you have to remember is the output is always input multiplied by whatever terminal is there for the gate of NMOS. Input multiplied by whatever term you are having for the gate of the NMOS. You need not look into the gate of the PMOS. So your B equation is nothing but A dot control. Suppose instead of control you are having some X or Y, say X is the value. So B is nothing but A dot X. Okay, so here it is control of C. So B is nothing but A dot control. It is read as A and control gives you B. So that is what you have to remember. I believe this is what we have seen for past transistors also. So same way you just have to write the equation. So this you need not worry about what value you are giving for the PMOS here for writing the output expression. So that is what the transmission gate truth table is about. So only when the control signal is active, input is transmitted on to the output. If the control signal is inactive, then the output is in a normal high impedance state. So there are different ways of drawing symbols for a transmission gate. I'm sorry. There are different ways of drawing symbols for a transmission gate. I've drawn few. So this is what we have seen. And this way also you can represent a symbol for transmission gate. So one thing you have to remember is that wherever you see a bubble, that is basically the gate of your PMOS. So that side is your PMOS. So here if you can see, here you can see a bubble over here. So this is actually your PMOS and the opposite side is your NMOS. So if we have a bubble over here, this is your PMOS and bottom you're having an NMOS, right? And the left is your input, right is your output. So this way also in some textbook you can see transmission gate symbol drawn like this, or this is the normally used symbol for transmission gate. On to the left hand side to the transmission gate circuit, this is what we have seen, PMOS and NMOS. Now PMOS and NMOS can also be drawn like this, that is an arrow pointing inwards is normally your PMOS, and arrow pointing outwards is normally your NMOS. So this way also you can draw the circuit representation of a transmission gate. That is up to you, whichever way comfortable you can draw the, you can draw the circuit. Okay, so these are the basic symbol of transmission gate. So we have just defined, or we have just seen what transmission gate is and how does it work. I mean, how you can explain the working of a transmission gate. So next what we need to see is I've told that transmission gate is also used to implement circuit just like past transistors. Okay, so how can that be done? So in order to understand that logic, it's actually very easy. In our last class, what we have seen is how to implement functions using a past transistor, right? So if you remember that steps very neatly, that can be used to easily implement logic functions using transmission gate. So I'm just trying to refresh. We'll just refresh it in 1 or 2 minutes. We have seen an AND gate circuit, the truth table of an AND gate circuit, and this is your past transistor implementation of an AND gate. So there also for an AND gate, we have seen two type of implementation, if you remember, wherein which the gate signal you have given, there are two literals, right? A and B, and the output is Y. So to the gate, you can either give A as a control signal, or to the gate, you can give B as a control signal. So depending upon that, you are having two types of circuits. So that is what I've drawn here. We've seen this, right? So this is actually your past transistor implementation of an AND gate. So how can you write the output Y? Output Y is nothing but B dot A plus, you're having two gates here. So it is B dot A plus, this is grounded. So 0 dot A bar. So output is nothing but B dot A or A dot B, which is your AND function. This circuit, the second circuit also functions as an AND circuit. Now how can we come into the equation of Y? Y is nothing but A dot B plus 0 dot B bar, which is Y is nothing but your A dot B. Now hope you remember how to implement this circuit. It's not a must that always when you have two literals A and B, always you need to give A to the gate and other input is B. It's not so. You can give B. It depends upon your wish how you're going to design. So how you design that? If you remember, if I want to keep my gate signal as A, my other input is actually B, right? So how did I get here as B and how did I get here as 0? So for that we have to look into the truth table. Am I right? Now, so A is in true form and also in a complement form. Two cases, A is in a complement form. That means A equal to A bar or A equal to 0. In other two cases, A is in a true form, that is A equal to A or A equal to A or A equal to 1. So these two cases we have to look, fixing A, we have to look how the output varies with the other input. That is a trick. Am I right? If you remember how the output varies with the other input. Right. So for A equal to 0 in both the cases, if you look here, when B is 0, output is 0. When B is 1, output is 0. So no matter what the input is, your output is always 0. So thereby you get the first NMOS circuit, that is when A is in a A bar form. So to the gate you are giving A as A bar. Then no matter what the value of B's, output is also always a 0. So what happens? You have to give a ground here because this 0 will be transmitted onto the output. So this is 0. Now what happens to the true form? When A equal to 1, what is happening? How the output varies with the other input. That is, when B is 0, output is 0. When B is 1, your output is 1. So that means what? Whatever is there in the other input is transmitted as it is to the output. Am I right? So when A equal to 1 or when A is in its true form, when A is in A form, then whatever is B is transmitted onto the output. So the other input is actually B itself. So thereby you can write this as B dot A plus 0 dot A bar, which is nothing but B dot A or A dot B bar. So that is in a nutshell how to implement any gates using pass transistors. Now, if that is clear to you, implementation of any logic function using transmission gate is also very easy. So this is your AND gate. Same way, let's say we try to implement a logic function, say 2x1 multiplexer using transmission gate. Okay. So for a 2x1 multiplexer, you know the output equation. You are having two inputs, you are having one output and one select line. So the output equation is, say, y equal to a s bar plus b into s, where a and b are the input, s is your select line. So output y equal to a s bar plus b s. So your corresponding pass transistor implementation is this. Output y can be read as a s bar plus b into s. So that is what your pass transistor implementation is. Now what we are interested in is how to implement the same circuit in transmission gate. So the idea is very, very simple. If you are thorough with implementation of an equation in pass transistors, then you can easily convert that circuit into transmission gate. Now how to do that? Now as I told you earlier itself, your transmission gate consists of an NMOS and PMOS in parallel. Am I right? So what you do is, given any equation, first it's very easy. What you can do is you can first write or implement that equation in pass transistor. So the equation what we got here is AS bar plus BS. So that equation I have implemented using a pass transistor. Right. Now this circuit, to convert that into in terms of transmission gate, what you just need to do is, for every NMOS, you just draw a parallel PMOS to it. Right. So how many NMOS are here? There are two NMOS. So you should draw two parallel PMOS. One PMOS to this NMOS and one PMOS to this NMOS. So that is what you need to do. Now if you remember the circuit diagram of transmission gate, your input and output of the PMOS and NMOS are shorted together. So here also the input is shorted here and the output is shorted here. For this PMOS that you're drawing here, input will be shorted here, output will be shorted here. So what is left? What is left is your gate terminal. So how to connect the gate terminal? So one important point of gate terminal is, say I'm replacing this NMOS with the transmission gate. That means I am having a NMOS and a PMOS here. So for this NMOS, if my control signal to the gate is S bar, then for the PMOS that I draw here, the gate signal will be S. So this gate signals of the PMOS and the NMOS should be complement of each other. So if I have S bar here, the other gate signal of the PMOS which you are going to draw here will be S. Same way, if I draw a PMOS here the gate signal of NMOS is S. So the gate signal of PMOS will be S bar. So that is how you can directly convert this circuit into a transmission gate circuit. So that circuit is here. Let's see whether we got it or not. This is a symbol of your transmission gate. So what we had is simply initially an NMOS. So A into S bar, this part only we had. Now what I told you, in order to convert this pass transistor into a transmission gate circuit, you just have to add one more PMOS over this and over this. So this section, what I add is I added one more PMOS. That is a bubble that you have here. So how will you connect the terminals? The input and the outputs are shorted. That is there. Now what is left is a gate terminal. Now how to assign polarity to the gate terminal is to here, to this NMOS, the polarity that I've given is S bar. So the PMOS which I'm connecting parallel to that the gate polarity should be inversion of this. So S bar inversion is S. So here if you have S bar to the PMOS, it is S. Am I right? So that is this circuit. Now for the other, the bottom one, what I have is an NMOS here, and for that NMOS I am giving the control signal as S. So that is what this one is, and B is my input, and I have to draw a parallel PMOS to the same NMOS. So that I have drawn here. So I put a bubble indicating it is a PMOS. And what is the control signal that I give to the gate of the PMOS? For the NMOS, the control signal is S. So definitely for the PMOS, it should be complement of each other. So what I've given here is S bar. If it is S here, so it is S bar. So that is your final circuit using transmission gate. So how you can write the output equation? The output equation you can write as the same way how you have analyzed for pass transistors. That is, you need not worry about writing the equation regarding the PMOS side. So you just need to look onto the NMOS side. So the output equation Y is nothing but A dot, in the NMOS side it is S bar. So A dot S bar plus B dot S. So your output Y is A dot S bar plus B dot S, which is nothing but equation of a 2x1 multiplexer. So that is your basic idea of implementing logic functions using transmission gate. You first easily draw the logic function using a pass transistor logic and replace that pass transistor with the transmission gate. And what you have to remember is the gate signals should be of a NMOS and PMOS should be complement of each other. So that way you can easily implement a transmission gate circuit. I believe it is clear. So we'll see one more example of an XOR gate. So XOR gate here, the function f is nothing but I've chosen signal A to drive the gate of the NMOS circuit. So f is nothing but B dot A bar plus B bar dot A, or A bar dot B plus A B bar, which is equation of an XOR gate. Now how to convert that into corresponding transmission gate circuit? You just replace this NMOS with the transmission gate, or how you can replace an NMOS with the transmission gate? By drawing a parallel PMOS with the NMOS. So you can short the input and output, and for the gate signal, what is the idea? You have to invert the whatever gate value you have given for NMOS, that value you have to complement and give as gate value to the PMOS. So if you see here, this is the corresponding transmission gate implementation of a XOR gate. So what happens here for a B? This is B dot A bar. So that B dot A bar is here. So this was your initial NMOS. Now in order to convert that into transmission gate to this NMOS, which is over here, I parallelly added a PMOS. So if this is A bar here, then this should be A. So complement of each other. So this is A. Similarly, for the second circuit, this is A B bar. Am I right? B bar A. This is coming from here. This line is coming from here. So this gate is actually A. So this is A B bar and A B bar plus A bar B. So the output is that of your XOR gate. I believe that is clear. If that is clear, you can easily implement any given logic function using transmission gates. Okay. So we'll just sum up, or we'll just try to define transmission gate once again with all the points that we have seen. So a transmission gate or a CMOS transmission gate consists of one NMOS and one PMOS, and that are connected in parallel, like what we have seen. Right. Then the gate, one more point we have seen is the gate voltages applied to these two transistors. These two transistors means the NMOS and PMOS, which are connected in parallel, are also said to be complementary signal. That is what we have seen. That is, if A is input of either NMOS or PMOS. Say if A is the input for a PMOS gate, then A bar should be the input for the NMOS gate. So the gate voltages applied to these two transistors are also said to be complementary signals. Then CMOS transmission gate, it actually is a switch. So it operates as a bidirectional switch between the nodes A and B. A is your input, B is the output, and which is controlled by the control signal C. C is the signal that you're giving to the gate, C and C bar. So CMOS transmission gate operates as a bidirectional switch between the nodes A and B, which is controlled by the signal C. So just the working, that is, if signal C is high, then both the transistors are on, then both the transistors are turned on and provide a low resistance current path between the nodes A input and the output, nodes A and B. If signal C is low, then both the transistors will be off and the path between nodes A and B, that is the input and the output, will be an open circuit. So this condition is also called as a high impedance. This is with reference to this diagram, that is, you are having an A and B, A as input, B as output, C or control as a gate signal. So as far as C value is 1, both the transistors are on, so A is passed on to the output. When C value or the control value is 0, both the transistors are off, so there is no connection between the input and output, so our output is normally in a high impedance state. So that is how you can conveniently explain or conveniently represent what a transmission gate is about. Okay, so we have just seen how to implement circuits using transmission gate also. We'll see one more circuit. Say I give an equation, implement F is equal to AB plus A bar C bar plus AB bar C using transmission gate. Okay, so in order to implement that, I just go one step further. If I see here, it is A, B plus A bar, C bar plus A, B bar, C bar. So for the first and the last term, A is common. So I just rearrange this and write as A bar. It is nothing but A bar, C bar. The second term I'm writing it as the first one. A bar, C bar plus A into B plus B bar C. So this is your equation. So I'm going to implement this equation using a transmission gate. So how many transmission gate do I basically require? I require a transmission gate to implement A bar, C bar. And very clearly, I require a transmission gate to implement B bar C. Then I have to do something with this B term, and then I have to do something for multiplication. So how can I implement? Right away, we'll come into the solution. So this is your circuit for this equation. Right. Now, how did this one come up with? First is A bar C bar. Let's look into A bar C bar. So you can implement this using a transmission gate. So C bar can be the input. A bar can be input to the gate of a NMOS, right? So that is what is written here. I have drawn a transmission gate here. So here is a bubble. So this is your PMOS and this will be your NMOS. So normally, if you remember how you write the equation is whatever value is coming on to the gate of the NMOS multiplied by the input, right? So what you require is A bar, C bar. So input I've chosen as C bar. That is your wish. If you want to choose here as A bar, then this will be C bar. So here it is input I've chosen it as C bar and the gate I've chosen it as A bar. So the output is nothing but C bar A bar or A bar C bar plus, then what are the terms? I have A into B bar, sorry, A into B plus B bar C. So what is it? If you look here, this is C multiplied by B bar. So this is C B bar or B bar C, this term plus B. So this is B is nothing but B dot 1. Am I right? So that they have implemented it something like this. That is B multiplied by VDD. VDD is 1, right? So 1 dot B bar. So what is this one? This point is actually C dot B bar plus 1 dot B or C dot B bar plus B multiplied by A. So this entire 3 transmission gate is for this expression. A into, that is A into CB bar plus B. Okay, so your final equation is C bar A bar plus A into CB bar plus B. So that is how you implement any equation using your basic transmission gate. I hope it is clear. And one more last thing is you have a universal logic circuit or logic module. 2 input universal logic module using transmission gate. So that means given any function, this circuit basically implements all the AND, OR, NOR, NAND, XOR and XNOR function, 2 input functions using transmission gate. Okay, now if you look here, we'll just analyze. This is one transmission gate and this is another transmission gate. So I have used 2 transmission gates. And if you look here, for this transmission gate, here you have the bubble. So this is your PMOS gate. So this is your NMOS gate. Similarly, for this transmission gate, here I am having a bubble. So this is my PMOS gate and this is my NMOS gate. The gate terminals are identified. Then this and this will be the input and the output. So this is the input for this transmission gate and this is the output for this transmission gate. This is the input for the second transmission gate and this is the output. So output both are shorted together. Okay. Now I have written the output function as function A comma B. Any value or any function between A and B. Okay. And the input to the first transmission gate is f of 0 comma b, so which is with respect to this truth table, and input to the second transmission gate is f of 1 comma b, that is with respect to this transmission and this truth table. Okay, now if I connect transmission gates like this, okay, so that means for the first transmission gate, the gate value for NMOS is A bar, right? You are giving here A bar, and for the second transmission gate, the gate value is A. Now, if I connect a circuit like this circuit can be implemented for getting any of these functions, provided you give the value of inputs as given in the truth table. Now, let's see how this works. So, let's say you talk about A dot B, which is your AND function. Okay, so when it is an AND function, what happens is f of 0 comma b, that is this input, should take the value that is provided here. Right, so f of 0 comma b, that is the first function, this value will be 0. Assume this is 0 over here. Now what about the other input? It is actually given here as b. So here you should give a b. So this is 0 and this is b. Now let's see what output you are getting over here. Right, so this is, what is this function? 0 multiplied by A bar plus B multiplied by A. Right. So this f of A comma B is 0 multiplied by A bar plus, here it is B multiplied by A, which is nothing but A dot B, which is nothing but AND function. So similarly, depending upon what value you give for both the inputs, according to this table, you will get this function. Let's say we try to explain for NAND gate. Okay, so for NAND gate, f of 0 dot b is 1. Right, 0 comma b. This function value you should give it as 1, and the second function value here you should give as b bar. So let's see what the function is. F of a comma b is nothing but 1 dot a bar plus, here what should you give? Here it is b bar, right? So b bar dot a. So this is what? 1 dot a bar plus b bar dot a, or a bar plus ab. Sorry, a bar plus ab bar, right? This is 1 dot a bar and this is b bar dot a. So a bar plus ab bar. So a bar plus ab bar can be written as like what we have seen for past transistors. A bar plus ab bar, you can simplify that using an identity. It is nothing but a bar plus a multiplied by a bar plus b bar. So a bar plus a is nothing but 1. So what you get is finally a bar plus b bar. So a bar plus b bar, by using De Morgan's law, it is nothing but a dot b the whole bar. So what you get is your NAND function. Similarly, you can work out the remaining things and see whether you are getting according to this particular truth table. So this is in general how you can implement a two input universal logic module using 2 transmission gates. Okay. So with that, I believe we can complete the analysis of, or we can complete the study of implementation of implementation of logic functions using transmission gates. Okay, so just a small comparison. So far we have seen pass transistors, we have seen complementary pass transistor logic, and we have seen transmission gate logic. So if I just compare between pass transistor logic and transmission gate logic, what are all the main points that you have to see? First major main point is we know that pass transistors cannot effectively pass 1 and 0 for NMOS and PMOS respectively. So that is a major disadvantage. But since transmission gate has both NMOS and PMOS in parallel, there is no issue like that here. So it can pass 1 and 0 effectively. So that is a major important or most important point or most important advantage compared to PTL for a transmission gate. So that is the first comparison. Another comparison that you can do is if you look into the circuit earlier, what we have seen, say for an XOR gate or for an AND gate, what we have seen is the number of gates required to implement any function in a pass transistor logic is obviously less. But for transmission gate, it is more. Say for example, we have seen the AND gate or an XOR gate. For 2-input XOR gate, in pass transistor logic, we just require 2 NMOS. Whereas if I just convert that into a transmission gate, you require 2 NMOS and 2 PMOS. So the number of gates is more for transmission gate, less for pass transistor logic. But that is, you can consider that is not much of a greater advantage given that even though the number of transistors is less, PTL fails in the point where it cannot efficiently pass 1 or 0. So that is not a big advantage to point out as it is, but it is just for comparison. The number of gates required to implement any logic function using PTL is actually less. Okay, so this is in short how you compare your pass transistor logic and transmission. We have seen, we have defined what a transmission gate is, and we also have seen how to implement basic circuits using transmission gate logic. Okay, so thereby we move upon the last part of transmission gate, that is you call that as a DC analysis of a CMOS transmission gate, or we are just trying to find out an equation for, or we are just trying to find out what is the total resistance of a transmission gate and why do we actually do that. The basic idea of that is, like initially when I told you, just like pass transistors, your transmission gate also can be used as a switch. So how efficient of a switch is actually a transmission gate? That can be understood from the concept of understanding the resistance of a transmission gate. So normally if you look for any switch, what can you say about the resistance of a switch? That is, irrespective of what is the value of the input or what is the value of the output, your resistance of your switch should always remain constant, right? It should not depend upon the input or the output. It should always remain constant. So that is an ideal switch. So whether your CMOS transmission gate behaves as an ideal switch, that is a point of thinking or point of analysis. So that is what we are going to do. Now that can be only done by looking onto the DC analysis or by looking onto each transistors and what are regions that it works. So that is what we are going to see by DC analysis of a CMOS transmission gate. Okay. So while doing that, what we do is we'll just analyze CMOS separately, we'll just analyze NMOS separately, PMOS separately. We are going to analyze it in terms of the regions of working. Okay. So this slide will come into that finally when we discuss. So when we talk about the analysis, first we talk about is the NMOS and the PMOS cara. Now we know that we have studied while looking onto a CMOS inverter, whether it is NMOS or whether it is PMOS, there is basically there are three regions of working for NMOS and PMOS. It is either in cutoff or it is in triode or ohmic or linear region, which is shown by here the slow rise. So it is either in triode region or it is in saturation region. So three regions of working: cutoff, triode, and saturation. And I believe you know what all these regions are. How does that happen? You know, the saturation region, the current actually saturates. The wave is actually flat. Triode region, there is a linear increase with respect to the increase in voltage, the current, there is a linear increase. So that is why it is called as a linear region, ohmic region, or a triode region. And the transistors are off, you call that as it is in a cutoff region, right? So that you have to remember. In order to analyze this one, these three regions you have to remember, or more clearly what you need to remember is the equations governing the entry into these three regions. Say for NMOS, when my VDS is less than VGS minus VT, you call that your NMOS has gone into a linear region. And for PMOS, when VDS is much greater than VGS minus VT, you call that it has gone into a saturation region. So these two equations for NMOS, you have to keep in mind. So similarly, you can write the equation for PMOS as, so for PMOS, for NMOS if this is VDS, then PMOS it will be VSD. Okay. So for PMOS, when VSD is greater or much greater than VSG minus mod of VT. You remember for PMOS, the threshold voltage is a negative value. So here it is mod of VT. Then the whole circuit or the PMOS goes into saturation. And when your VSD is less than VSG minus mod of VT, then your PMOS goes into linear region. Okay. So these equations you have to remember to analyze the working DC analysis of transmission gate. So we'll start our analysis. So what I've done is I've drawn the transmission gate circuit over here. So you have to remember the case which we are going to analyze. The case is where both the transistors are on and both the transistors are off. It is obviously in the cutoff region. There is no connection between the input and the output. So there is no point to analyze, right? So we are going to see when both the transistors are on. Transistors are on means to the NMOS you are giving G value as VDD or logic high. For the PMOS, your gate value is 0. Okay. So both the PMOS is on, NMOS is on, and also the input that I'm providing is, initially input was 0 and I'm providing a VDD. So the output that we expect to get is VDD, right? So that is a condition. So this is the source of PMOS, drain of PMOS, drain of NMOS, and source of NMOS. So this is how it is connected. So we'll start with analyzing the NMOS first. So what are all the regions of working under this input condition? This does the NMOS go through. So in order for us not to forget, I've also copied the linear and the saturation region equation. So first what we do is, what all terms are here? There are three terms, which is VT, VGS, VDS. Am I right? So VT, we can choose it as a standard value, that is around 0.7 volt. Now what is VGS? What is VDS? We need to write an equation for both VGS and VDS depending upon this particular circuit. So let's write that. So for NMOS, we'll write an equation for VDS and VGS. So what is VDS? VDS is nothing but VD minus VS. So this is your NMOS. So VDS is VD minus VS. So VD is what? VDD. VD is the input that you're giving for drain side. So that is nothing but VDD. VS is the output side. So I write that as conveniently V out. So VDS is nothing but VD minus VS, which is VDD minus V out. Same way VGS is nothing but VG minus VS, which is VDD minus V out. VG here is VDD, VS is V out. So VGS is also VD minus V out. Okay, so both VDS and VGS equation are the same. So we've written equation for VDS and VGS. Then what? So we also know that the NMOS is on for VGS greater than VTH, right? For any gate to source voltage greater than your threshold voltage, your NMOS is on. So you concentrate on this equation. VGS is greater than VTH. So what I do to this equation, I just substitute the equation of VGS from here. So what is my VGS? It is VDD minus V out is greater than VTH. If this is the condition, then your NMOS is on. So let's try to rearrange this equation in terms of something on left hand side as V out. So I take the term this side and I try to remove the negative sign. So if I rearrange it and write, I can say that my V out, when it is less than VDD minus VTH, I bring it over here and change the sign. So this symbol is changed and this one is also changed. So you can write this equation and see. So if you rearrange in terms of V out, I can say V out when it is less than VDD minus VTH, your NMOS is on. You've written the condition for NMOS to be on, right? So when V out is less than VDD minus VTH, your NMOS is on. So when is NMOS off? Obviously, if you reverse this equation, that is when V out is NMOS is off for V out is greater than VDD minus VTH, right? From this, what you got as when V out is less than VDD minus VTH, your NMOS is on. So obviously, when V out is less than VDD minus VTH, NMOS is on, and when a V out is greater than VDD minus VTH, your NMOS is off. So that we have got. Okay. So when NMOS is off, that is no point. You can say clearly it is in the cutoff region. Now, when NMOS is on, there are two possibilities for this. When the transistor is on, it can either be in a linear region or it can go into a saturation region. So when this is on here, what region is it actually working on? That also we need to find out. Am I right? So for that, we take help of these two equations. So it is either linear, for this equation it is linear, for this one it is saturation. Am I right? So if you look here, when VDS is less than VGS minus VT, it is in linear condition, otherwise it is in saturation condition. So according to our case, we'll see which of these two equations are true for us. Am I right? Whether VDS is less than VGS minus VT or whether VDS is greater than VGS minus VT. If any one of these conditions is true, that is a region where your NMOS is actually working on. So we look onto the equation of VDS and VGS. If you look here, both the equations are same. Am I right? So VDS is equal to VGS, right? So on basis of that, can you tell me which equation is true over here? Say for simplicity's sake, assume your VDD is 5 volt, okay? And assume your V out has come into some 0, or let's say V out is initial, you are taking a condition where V out is equal to 1 volt. So this is 5 minus 1, which is 4 volt. So assume your VDS is equal to 4 volt, which is the same as VGS as per this equation. Both are 4 volt. Now, which equation is true over here? So 4 volt is 4 volt less than 4 volt minus, what is VT? VT, assume it as a standard value 0.7. So is that true or this one true? 4 volt less than 4 minus 0.7, that is 3.3. Is this true? This is not true, right? This is true. 4 volt is greater than 4 minus 0.7. So 4 volt is greater than 3.3 volt. So this equation becomes true. So that means your NMOS, when it is on, it is actually in a saturation region. So NMOS is on, so it is in saturation region. So that is what you get. For this set of inputs, for a value V out less than VDD minus VTH, NMOS is on and it is in saturation. For a value V out greater than VDD minus VTH, your NMOS is off. So that is what we have concluded. So those are the two regions of working for a NMOS over here. Now I tried to plot that as a graph here. So towards x-axis, what I get is VO or your V out. Okay, so I've marked 3 points over here. This is a mod of VTP. This is mainly for analysis of PMOS. And the one which relates to NMOS is VDD minus VTH. That is what we have seen here. VDD minus VTH and towards the VDD. The maximum output value that you can have is towards the VDD. Am I right? So what we have seen is NMOS is off for, this is your output V out, for V out greater than VDD minus VTH. So this is your VDD minus VTH. So if V out goes beyond VDD minus VTH, your NMOS is off. Right. So when it is less than VDD minus VTH, NMOS is actually on and also it is in saturation. So NMOS is in saturation over here. I believe it is clear. So for a voltage value V out greater than VDD minus VTH, your NMOS is off. Less than VDD minus VTH, NMOS is on. On means it is in saturation region. That we have concluded from the equations over here. So that is the analysis of NMOS. So NMOS actually goes through saturation and cutoff. That's what here is. Right. Same way you can analyze for PMOS. So the same circuit and the equation for saturation and linear is being copied out here. And let's say same way we are trying to analyze the PMOS. So for PMOS, here you have which all terms you have VSD, VSG. So you have to write the equation for VSD and VSG. So VSD is nothing but VS minus VD. Am I right? So here it is VS and this is VD. So here input is VDD and VD here is Vout for a PMOS. So VSD is nothing but VDD minus Vout. So that equation we have written here. And now what is VSG? VSG is nothing but Vs minus Vg. Now remember PMOS is on, that means gate terminal you are giving it as a 0 volt, right? So this is Vs minus Vg, that means VDD minus 0, which is VDD itself. So we got the equation for VSD and VSG. Now one thing you have to note here is I'm making your gate terminal as 0. Am I right? So your VGS, like what you say for NMOS, VGS means VG minus VS, which is 0 minus VDD, which is minus VDD. So you're having a negative voltage at the gate for gate to source voltage for the PMOS. So this PMOS is always on. Or more clearly, you're applying a 0 volt to the gate. So this transistor, PMOS transistor is always in a on state. So for the analysis for this set of input conditions, our PMOS is always on. It is not going into cutoff. That is the first thing what you have to remember. So PMOS is always on. So that means it is either in the saturation region or in the linear region. So it is not going to cut off as per our equation. So we need to find out which region of working does it fall on, whether it is in the saturation region or whether it is in the linear region. For that, we take help of these two equations, right? So according to our equation, when VSD is less than VSG minus, it is in a linear region. Other way around, it is in a saturation region. So we take the equation first and then we substitute for VSD and VSD from these two equations here. So what I get here, VSD is nothing but VDD minus Vout is less than VSD is VDD minus VTH. Then this is in linear region. So I can rearrange, I have VDD common here. So I can cancel that out and I can remove the negative sign. So when I rearrange, what I get is when Vout is greater than VTH or VT, the threshold voltage, the circuit or the PMOS goes into a linear region. So obviously when Vout is if Vout is greater than VTH, if it is linear, then when Vout is less than VT, it should be in saturation. That you will get it by directly substituting in the first equation. So we got the expression for which case it is linear and which case it is saturation. So thereby we'll come into that diagram again. On top, what we have written is for NMOS, which we have seen earlier. So PMOS is always on. So what happens? PMOS is a linear region where Vout is greater than VT. So the benchmark what I put here is VT or VTP. So for a Vout greater than VT, so these three, this is the point where Vout is greater than VT. So for that entire region, your PMOS is in linear region of operation. And when Vout is less than VT, it is in saturation. So that is what is shown here. Okay. So this completes the analysis for if I give the input as VDD and make both the gates active. Right. So your NMOS and PMOS actually goes through these three regions of working. So with that in mind, what we can do same way here, the analysis what we have done is for input is VDD. Okay. Now same analysis can be done for the input as, this is for input as VDD. This is the analysis that we have done just now. Same way, using all those equations, you can analyze for input to be 0 volt. Okay. So in that case, you will get your regions of operation like this. That is left to you as exercise. We don't have much time to analyze that. So please go through that and see whether you're getting this one. Just like how we have analyzed for this one, you can do the analysis for this one, this also. So let's concentrate on what we have derived. So this is what we got. That is, our condition is we are making both the gates active and we are providing the input as VDD. So if that is the case, these are the regions, or this is how your depending upon the output voltage, the regions of working of NMOS and PMOS. NMOS is saturation, saturation, cutoff, PMOS is saturation, and then after that, after VTP, it goes into a linear state. Okay, now why we have learned all these things? We have learned all these things basically in order to get an idea about the current equation, right? If you remember, when we studied the CMOS inverter equation, current equation, which is mu n C 1 by 2 mu n Cox W by L into VDS minus VGS minus VT, the whole square, that equation, if you remember, for saturation, you are having a different current equation. For cutoff region, obviously you have a different equation. For linear region, you have a different current equation. So for each region of operation, you are having a different current equation. Now, why do we require that current equation? Remember, we have done all this analysis to find out the total resistance of a CMOS transmission gate. Am I right? So before we look into this equation, we'll just come into this transmission gate. So we are trying to find out the total resistance of this particular transmission gate. So what is actually resistance? Resistance is nothing but voltage by current. Okay. So that current, voltage by current, that current varies depending upon the different regions of working of the transistor. So that is the reason why we differentiated that into different regions. So the total current of the transmission gate is nothing but the current through the PMOS plus current through the NMOS. So that is what is written here. ID is ID of the NMOS plus ID of the PMOS. Right. So the equivalent resistance is nothing but voltage by the current. Okay. So if I talk about the NMOS here, our equivalent resistance or the resistance of NMOS is nothing but the voltage by the current. So voltage means VDD minus V out, input minus output, right? VDD minus V out by ID, right? That is a resistance of an NMOS. Same way, resistance of PMOS is VDD minus V out by the current through the PMOS, ID SP. So the total resistance is these two transistors are in parallel. So obviously the resistance is parallel, Rn parallel to Rp. So that is your final resistance of the circuit. Now why we are looking onto this is because we are just trying to prove that whatever be the value of input and output, your total resistance of this circuit remains always constant. If that is the case, then we can say this transmission gate works as an ideal switch. So all the pain we have gone through in analyzing this and this is to find out the resistance. Okay, the final total resistance. So that resistance can be got by resistance is nothing but voltage by current, and that current equation varies depending upon each region of working. Right. So that is the main aim of going through all this part. So we have a total current equation here and the resistance equation here. So based on that, say for different regions, say region 1, region 2, region 3. So region 1, NMOS is in saturation, PMOS is also in saturation. So what is the resistance of the NMOS transistor? It is nothing but VDD minus V out by IDS, ID current, right? So ID current of N is in saturation. So you write the current equation for N here. Same way, PMOS is also in saturation. So the resistance is this voltage divided by the current equation. The current equation is 1 by 2 mu n CMOS or Kp. So that 1 by 2, that 2 will go upwards. So these are the corresponding resistance equations. Now you need not worry about looking onto this big equation, because this equation you have already derived. What you just need to do is substitute the value of ID for saturation, ID for cutoff, ID for saturation, and ID for linear. For cutoff there is no ID, right? So that if you just simply substitute, you will get these equations. Okay, so these equations are there. This is left you to just read what is these equation. Now we are worried about the total final resistance. So for each region, the total resistance is a parallel value of this and this. For region 2, it is a parallel value of this and this. For region 3, it is a parallel value of this and this. Okay. So what I do is I just try to plot the resistance that we got from these equations. So your plot of the resistance, final resistance, looks something like this. Okay. So what you see on the, as a red line is basically the resistance of the PMOS. What you see in the black line is actually the resistance of your NMOS. And what you see, the green line is actually the parallel combination or the effective resistance of a transmission gate. Okay, so as you can see from the equation, if I try to plot, the resistance of a PMOS is actually decreasing and the resistance of NMOS is actually increasing. So when I talk about the parallel combination R equivalent of N to R equivalent of P, we can say that your resistance, total equivalent resistance is actually remaining constant, right? So that is a good sign. That is what we want, right? I told you initially itself, for it to behave as a proper gate, sorry, proper switch, the output, the equivalent resistance of the circuit should be constant. It should not depend upon or should not vary with the input and the output. So that is what you get for a transmission gate. So thereby, what we can say is conveniently, or we can say very surely that this transmission gate can act as an ideal switch, since the resistance, equivalent resistance of the transmission gate basically remains constant, almost constant throughout. Okay, it doesn't vary with respect to the input and the output. So when we conclude that point, your DC analysis of transmission gate is over. So what we have seen is the effective resistance is basically constant throughout. Therefore, it is more ideal switch compared to a pass transistor logic. That is, the resistance is basically not varying depending upon the input and the output voltages. So you can call this as a ideal switch. So that concludes your analysis, DC analysis part of your transmission gate. Thereby, with that, actually your module 4 of VLSI is also over. The analysis of transmission gate is also over. That means so far what we have seen in module 4 is, according to your syllabus, it is pass transistor logic, complementary pass transistor logic, transmission gate, and realization of logic function. So these are what you have in your fourth module. It is actually a very small module and a very easy one compared to all other modules. So in pass transistors, what we have seen is how to implement the logic function, the characteristics of pass transistors as in the advantages, disadvantages, and also the cascading, how you can connect the pass transistor. That point we have seen in the first part, that is part 1 of VLSI module 4. And also you've seen the complementary pass transistor logic, where there you've just seen the how to implement the logic function, right? No more other point in that. And today in this class, what we have discussed is the transmission gate, how to implement logic functions using transmission gate, and finally the DC analysis or the equivalent resistance analysis. So as such, this sums up what all you have to study in your fourth module that we have concluded, or sorry, that we have completed in 2 classes. And just like what we have seen in the last session, from the university question papers, I've just copied the questions related to transmission gate. So one question is, you have to differentiate the pass transistor, CPTL, that is complementary pass transistor logic, and transmission gate. You just have to compare these 3, and they've got 5 marks. They've given 5 marks for that. And next question is, what is a transmission gate? Draw XOR gate using transmission gate. That is a direct easy question. For that, you are having a 5 mark. Another question is, explain the demerits of pass transistors, how it can be remedied. So what is a major demerit of pass transistors? That is, it cannot pass a good 1 or good 0. So that you have to explain how it is not passing a good 1 or good 0. And the way which you can remedy that is using a transmission gate. So you have to define what is a transmission gate, how it passes a good 0 or good 1. So that is, they've given 7 marks for that question. If you answer, you will get 7 marks. And another question is, implement the following functions using pass transistors and transmission gates. So it is A or B, X or X nor B. Both are 2 input functions and very easy to implement. And they've given 8 marks for that. So you can easily score 8 marks in that also. So these are the some questions related to transmission gate that we have seen in the university question papers. Okay. So for this topic, that is transmission gate, is neatly explained in your reference textbook, 𝐂𝐸𝐿, Digital Integrated Circuits Analysis and Design by 𝐂𝐸𝐿. That is a good read book. And also for preparing the PPT, I have referred an NPTEL lecture, and the link is available as given here. So I believe the concepts are clear. I've done justice to module 4, and hope you can study this easily. and it's over to you. My session is over for today. Hello?
Thank you, ma'am. Thank you for the valuable session. Ma'am,
Okay.
we have few questions.
Okay.
One of the question is, when
Yeah.
both transistors are on in transmission gates, how
Yes.
can we ensure that 0 will pass through NMOS and 1 will pass through PMOS?
Yes. That is a valid question. So if you look into the circuit diagram of a transmission gate, okay, you can take here. This is a circuit diagram of a transmission gate. So what happens is you're making both the gate active. So NMOS and PMOS is 1. Okay, so suppose you're giving an input as VDD or logic high. So, sorry, you're giving the input as logic high. Okay, now we know that you have a CMOS, I mean NMOS here. NMOS will switch off as soon as this output capacitor charges up to VDD minus VTH, right? So by switching this off, or when it switches off, that means this gives a high resistance path. So there is no way this entire VDD can pass through NMOS to the output. But what happens to the PMOS? PMOS is always on. Am I right? So it doesn't depend upon this value of VDD. So what happens is the entire VDD can go through PMOS to the output capacitance, and it can charge up to, this provides a low resistance path to charge up to VDD. So that way we can ensure you are getting entire VDD or logic 1 through PMOS. Now when I have a logic 0 over here, what happens is this output capacitor discharges to 0, right? So what happens here is your PMOS, once the voltage becomes lower than the threshold voltage, your PMOS will be switched off. So switched off means this offers a high resistance path, but always in this case, depending upon the VGS and VDS equation, your NMOS will be always on if I give a 0 over here. So when it is always on, there is a discharge path. This capacitor can entirely discharge through this path to 0. So you will get a perfect 0 here. So this is the path for 0 and this is the path for 1. So thereby you can ensure you are getting a proper 1 and proper 0. I believe it is clear.
Ma'am, we have another question.
Yes.
It's a request to explain transmission gate truth table once more.
Transmission gate truth table.
Truth table.
Yeah. So this is a transmission gate truth table. So here I'm having an input as A, output as B. Your where you have a bubble here. So this is my PMOS. To PMOS I'm giving control bar, and for NMOS I'm giving control. Okay. So for this transmission gate to be working or active, I should activate both the NMOS and PMOS. I should make on the NMOS and PMOS. So to do that, what I should give is, to the NMOS gate I should give the control value as 1 and the control bar as 0, right? So this is on when my control value is 1, right? So control is 1 means NMOS is on, so control bar becomes 0, so PMOS is also on. So when control is 1, what you give as input is reached as output here. So that is what is written in the truth table here. So when control is 1, the input, if it is 0, that you get as output 0, just like how I have explained earlier. And when being the control 1, if I give 1 as input, that 1 is obtained as output through the PMOS. Okay. Now what will happen when your control value is 0? Control value 0 means to the gate of the NMOS you're giving a 0, and to the gate of a PMOS you're giving a 1. So both the transistors are on, so there is no connection between the input and the output. So no matter what you give as input, whether 0 or 1, your output will always remain in a high impedance state. That is what your truth table of transmission gate is. I hope that explains it.
Yes, ma'am. Ma'am, we have another question. Are we considering only NMOS while summing in the transmission gates?
Yes, we are considering only NMOS while summing in the transmission gate. So just like what we have considered for past transistors. So here itself, we can write the Boolean expression B as A dot what value you given as a gate signal to the NMOS. So A dot A and control, A and control. That is how you should consider, or say if this equation itself, how we can write this equation is nothing but this is your NMOS part. So C bar dot A bar plus C dot, these are the NMOS part. Top you are having the PMOS part. So you just need to look onto the NMOS part. So C bar dot A bar plus C dot B bar plus 1 dot B multiplied by A. So we have to always look into the NMOS part. No need to look onto the PMOS part. You may get confused. I hope it is clear, that point is clear. Any more questions?
Ma'am, one more question we have to summarize the function implementation once again. And the implementation of logic gates.
Function, okay. Implementation of logic gates. What you can do, the step. I believe you are asking for the step. So
Yes,
what you have to do is basically once you're thorough with implementing the logic function using pass transistors, you can easily implement it using a transmission gate. So what you have to do is, this is an XOR function. So XOR function, the truth circuit diagram using pass transistors, you draw it. Now what you do is, wherever you're having an NMOS, you replace that part with the corresponding transmission gate. By transmission gate, what I have is an NMOS and PMOS in parallel. So I already have an NMOS here. So in order to replace this by a transmission gate means I have to include a PMOS in parallel, right? So the connection, there is no confusion. For a transmission gate, the input and the outputs are shorted with that of the NMOS. Now what remains is, what signal do we apply to the gate of the PMOS that we had here. So from the explanation of the derivation, we've seen that the gates are always complement with each other. So if I add for this NMOS, I've replaced that with the transmission gate. So what value should I give it to the gate of the PMOS? Am I right? So whatever value you've given to the gate of the NMOS, the complement should be given to the gate of the PMOS. So here for the gate of the NMOS, I've given A bar. Am I right? This is a NMOS here. So for that, I've given A bar. So for that PMOS which I draw parallel to the NMOS, for that gate, I've given I should give the complement of A bar, which is nothing but A. So the basic idea to sum up is, replace your NMOS with the transmission gate and short the input and the output. Now the gate value should be connected in given in such a way that the gate for NMOS is complement for the should be complement of gate for the PMOS. I believe it is clear.
Yes, ma'am. Thank you for the session, ma'am. It was an enlightening session. We are now over with the Q&A session.
Okay, thank you, and all the best for your exam.